Good afternoon all. So we are going to start the session. This is week 11 session, sensor and actuator course, and I'm ARPITA BISWAS. I'm from IT Jodhpur, and this is about me. I'm ARPITA BISWAS, a student of a PhD student from IT Jodhpur in electrical engineering department, and this is my educational background that I did my MTech in micronanoelectronics from IIIT Jabalpur, and I did my BTech in electronics and communication engineering from West Bengal University and Technology, and this class schedule is every Tuesday 7 to 9 p.m. So let's wait for 2-3 minutes to join the students, then we will start our session. So we are going to start this session. This is question number 1. The flexible substrate used to fabricate the electrochemical sensor for understanding the tissue property was, and if you have any question then you can directly ask me. And we are already the Professor Hardikji Pandya shared all the lecture video. So here we are going to discuss about some of the question. So the first question is the flexible substrate used to fabricate the electrochemical sensor for understanding the tissue property was. The first option is the PET, the second option is the PTFE, and the third option is the PDMS, and the fourth option is the glass. So take your time and then try to solve the question. So the right option is the third option, the PDMS. So the flexible substrate which is used to fabricate the electromechanical sensor for understanding the tissue property was PDMS. So next we are moving towards the question number 2. So the question number 2 is evaluate whether the below statement is true or false. So the statement is the piezo-resistive layer was made using the P.PSS. So the is it right or it is false? So what is the statement? You can go carefully. And the statement is the piezo-resistive layer was made using the P.PSS. So the right option is it is true. The statement is true. Next we are moving towards the question number 3. Evaluate whether the below statement is true or false. P.PSS is a conducting polymer. So this statement is true or false. So try to solve the question. Evaluate whether the below statement is true or false, and that statement is P.PSS is a conducting polymer. So the right option is option A, true. So P.PSS is a conducting polymer. Next we are moving towards the question number 4. The electromechanical sensor discussed used several materials such as PDMS, chromium, gold, P.PSS, SU 8, etc. Which of the following statements regarding the process flow for realizing the sensor are correct? So the first statement is the PDMS layer was deposited on the silicon substrate using the spin coating. And the second statement is the P.PSS layer was deposited on the substrate after the chromium gold patterning using E-beam evaporation. So the first option is only 1, the second option is only 2, and third option is both, and the last option is option D, none of the above. So go through the question carefully and then try to solve the question. Once again we are going through the question. The electromechanical sensor discussed used several materials such as PDMS, chromium gold, P.PSS, SU 8, etc. Which of the following statements regarding the process flow for realizing the sensor are correct? So first option A, first statement is the PDMS layer was deposited on the silicon substrate using the spin coating. And the second option is the P.PSS layer was deposited on the substrate after chromium and gold patterning using E-beam evaporation. So what is the right answer? Take your time and then try to solve the question. So the right option is only A, only one. So the PDMS layer was deposited on the silicon substrate using the spin coating is the right answer. And and is the right statement. And the P dot PSS layer was deposited on the substrate after chromium and gold sputtering using E-beam evaporation is not the right statement. So the right option is only one. Next we are moving toward the question number 5. AC weight pillars are formed in the electromechanical sensor to act as force transfer structure. Which of the following statements are correct regarding the process flow for AC weight? The first option is the AC weights needs to be patterned using a special type of photoresist. Second option B is AC weight itself acts as a negative photoresist. And the option C is the process flow for patterning and developing the SU weight is same as that of the photoresist. And the last option is the soft bake time of SU weight is fixed irrespective of the thickness. So carefully go through the question and then try to solve the answer. So what is the question now? SU weight pillars are formed in the electromechanical sensor to act as force transfer structure. Which of the following statements are correct regarding the process flow for AC weight? The first option is AC weights needs to be patterned using the special type of photoresist. And the option B is AC weight itself acts as a negative photoresist. Option C is the process flow for patterning and developing the AC weight is the same as that of the photoresist. And the option D is the soft bake time of AC weight is fixed irrespective of the thickness. So what is the right answer? AC weight pillar are formed in the electromechanical sensor to act as force transfer structure. Which of the following statements are correct regarding the photoresist, regarding the process flow for AC weight? So yeah, we so the right option is option B. AC weight itself acts as a negative photoresist. Next, we are moving toward the question number 8. Evaluate which of the following statements are true regarding the electromechanical sensor to measure the tissue properties. First statement is AC weight pillar are coated with gold and pattern using the lift off technique. Second statement is the contact lines from the contact pads to the sensing layer is made like instead of straight to mit, uh, mitigate stresses from the flexible substrate. So what is the right answer? Only one, only two, and option C is both 1 and 2, and the option D is neither 1 or not 2. So evaluate which of the following statements are true regarding the electromechanical sensor measure the tissue property. So try to solve the question. So the right option is both A and B. It means option C is the right answer. Evaluate which of the following statements are true regarding the electromechanical sensor. Electromechanical sensor to measure the tissue properties. So first option is AC weight pillars are coated with gold and patterned using lift-off technique. The second statement is the contact lines from the contact pads to the sensing layer is made like instead of straight, mitigate stresses from the flexible substrate. So both option 1 and 2, statement 2 is right. So option C is the right answer. Next we are moving towards the question number 7. Which among the following material can be used to making microfluidic channel? First option is PDMS, second option is PMMA, and the third option is paper, and the fourth option is all of the above. So go through the question carefully and then try to give the answer. So the right option is option D, all of the above. So question is which among the following material can be used for making the microfluidic channel? So using the PDMS, we can use for making the microfluidic channels. Also PMM also used for making the microfluidic channels, and so also there are some paper based microfluidic channels are present. So the right option is option D, all of the above. Next we are moving toward the question number 8. What is the name of the tool technique in Autodesk invented to make a 3D model from a 2D drawing? So first option is protrusion, and the second option is the extrusion, and the option C is the combining, and the option D is the elongations. So go through the question carefully and then try to give the answer. So the question is, what is the name of the tool or technique in Autodesk inventor to make a 3D model from a 2D drawing? The first option is the protrusions, and the second option is the extrusion, and option C is combining, and the last option is elongations. So the right option is the option B, extrusion. So what is the name of the tool or technique in Autodesk Inventor to make a 3D model from a 2D drawing is extrusion. Next we are moving the question number 9. What is the name of the extension? What is the name for the file extension for the part file in Autodesk Inventor? So the first option is .part, the second option is .stl, and the third option is .ipt, and the fourth option is .sldprt. So go through the question carefully, take your time, and then try to give the answer. So the right option is .ipt. What is the name for the file extension for the part file in Autodesk Inventor? The file name is .ipt. The option C is the right answer. Next we are moving towards the question number 10. The question is name of the tool to create a mirror feature which respect to a plane or surface is called. First option is mirror, the second option is copy, and the third option is pattern, and the fourth option is import. So try to solve the question. Name of the tool to create a mirror feature with respect to a plane or surface is called. First option is mirror, the second option is the copy, third option is pattern, and the fourth option is import. Please try to solve the question. So the right option is option A, mirror. Name of the tool to create a mirrored feature with respect to a plane or surface is called mirror. Next, we are moving toward the question number 11. How many dimensions are need to constrain a rectangle which is created using a rectangle tool? Starting at the origin in Autodesk Inventor. So, the first option A is 4, B is 3, and option C is 2, and option D is 1. So go through the question carefully. How many dimensions are needed to constrain a rectangle which is created using a rectangle tool? Starting at the origin in Autodesk Inventor. Option A is 4, option B is 3, option C is 2, and option D is 1. So what is the right answer? So the right option is option C, 2. How many dimensions are needed to constrain a rectangle? There are 2 dimensions are needed to create this using a rectangular tool straight at origin in Autodesk Inventor. So right option is option C. And then we are moving toward the question number 12. What is the file extension of the assembly file in Autodesk Inventor? So the first option is .sldprt, and the second option is .sti, .stl, and the third option is assembly, and the fourth option is .iam. So what is the file extension of the assembly file in Autodesk Inventor? Option A is .sldprt, option B is .stl, option C is .assembly, option D is .iam. So what is the right answer? So the right option is .iam. Option D is the right option. Next we are moving toward the question number 30. The use of the piezo register was to understand. So option A is mechanical property of the tissue, option B is elasticity of the tissue, option C is stiffness of the tissue, and option D is all of the above. So the use of the piezo register was to understand the mechanical property of the tissue, the elasticity of the tissue, or the stiffness of the tissue, or all of the above. So go through the question carefully and then to try to give the answer. So the right option is all of the above. The use of the piezoresistor was to understand mechanical property of the tissue, also the elasticity of the tissue and stiffness of the tissue. So right option is all of the above. Next we are moving toward the question number 14. The biosensor with interdigited electrode was to understand the dash properties of the tissue. So the question is, the biosensor with an interdigited electrode was to understand the dash property of the tissue. So fill in the blanks. Uh, which property of the tissue is measured by the interdigited electrode? The biosensor with the interdigited electrode was to understand hello. Am I audible, Preetham? Hello. Am I audible? So the right option is electrical property of the tissue. Next we are moving toward the question number 15. For patterning the chromium and gold, which process we have to follow? So go through the question carefully. For patterning the chromium and gold, which process we have to follow? At first we have to know why we deposit the chromium. Actually the addition of the gold is not that much good. That's why we have previously deposited the chromium 20 nanometer to 30 nanometer chromium, then and above the chromium we have to deposit the gold to increase the addition, and it is thickness near about the 200 nanometer. So we, for patterning this chromium and gold, which process we have to follow? So patterning the chromium and gold, we have to follow the lithography process. Like we have to at first we have to deposit the chromium, then on the chromium we have to deposit the gold, 20 nanometer of chromium and 200 nanometer of gold. Then we go for the lithography process, and what we did in lithography process, at first we coated this chromium gold using the photoresist, and then we go for the soft bake process, like 90 degrees centigrade for 1 minute. Then we after the soft bake process we go for the UV, we load the mask, and using the mask we then UV we go for the UV exposed, and based on the based on the photoresist and the mask pattern, the pattern is generated or the pattern is transferred on the photoresist, and after that after that we go for the development process. And in the development process, if it is negative photoresist, then the underlying then the covered portion is become soluble, and the exposed portion become then the exposed portion become stronger or harder. And for the positive photoresist, the exposed portion become easily soluble, and the covered portion become stronger or harder. And then after the after the development process, we go for the etching process. So we use at first there was the upper layer is gold, and then below chromium. So we use the gold agent, and then we use the chromium agent. So this is the process. And after the etching we go for and in between there is a hard bake hard bake process after the development, which is 120 degrees centigrade for 1 minute, and after the aging we can after the aging we can see that the pattern is transferred on the chromium gold. So this is the photolithography stage which we use for patterning the chromium gold. So next we are moving towards the question number 16, how to remove the photoresist. So after the aging process there is a photoresist present upper side of the chromium or gold, and which is remaining portion and which actually used as a masking layer. So how to remove that photoresist? So for removing the photoresist, we can use the IPA or acetone as the remover of the photoresist. So if we use a device on the IPA or IPA or the acetone, then we go for the ultrasonication process. We can easily remove the photoresist. Then the next question is question number 17 is how to remove the P dot PSS. So the P dot PSS is a conducting polymer, and also it is used for the chemiresistive sensor. So how to remove this P dot PSS? So to remove this P dot PSS, we can use the etching process like RIE, reactive ion etching. So by the reactive ion etching process, we can easily remove the P dot PSS. And we are moving towards the question number 18. So question number 18 is, what is the difference between positive and negative and SU 8 lithography process? So when we go for the positive and negative when we use the positive and negative photoresist, in that case, at first we go for the soft bake. We coated the wafer or device use of photoresist, positive or negative photoresist. Then after that, on that positive photoresist, we go for the soft bake process, which is 90 degrees centigrade and for 1 minute. Then we go for the UV expose. Then after UV expose, we go for the development process, and after development we go for the hard bake process, which is 120 degrees centigrade for 1 minute. Then after the hard bake process, we go for the etching process. And for when we use the SU8, SU8 is a negative photoresist. It acts as a negative photoresist. So for that case, SU8, at first we go for the soft bake, and the temperature, here is the difference. For the soft bake process, for positive and negative photoresist, it is 90 degrees centigrade for 1 minute. But for SU8, the temperature is 65 degrees centigrade, and the time is depends on the thickness of the SU8. And then we go for the hard bake process, which is 90 degrees centigrade for, and also the time is depends on the thickness of the SU8. Then after that, after SU8 deposition, and after that we go for the UV exposed, and after UV exposed we go for the development process. And after development process, we also here also the baking process, and also here the one baking process is there, and the temperature of this baking process is 120 greater than 125 degrees centigrade, and also the time is depends on the thickness of the SU8. And then we go for the etching process. So there is the difference, like soft bake process temperature difference, and also the hard bake process. Next we are moving toward the question number 19. The following statement is true or false. For flexible MEMS device, SU8 acts as a electrode when it's covered with the gold. So some MEMS device SU8, there is a gold electrode, and then SU8 is deposited, and after the SU8 deposition also it is coated with the gold. So it is acts as a electrodes or not. So the statement is true or false. Take your time and then try to solve the question. it is true. The statement is true. For flexible MEMS device, AC weights acts as a electrode when it's coated with gold. Next question, we are moving toward the question number 20. So the P dot PSS and electrodes are separated by dash. So fill in the blanks. The P dot PSS is the conducting polymer. Also, it is used for the resistive sensor, for chemi-resistive or the resistive sensor. And electrodes are separated by. So when we go for the when we make the electrode on the P dot PSS, the conducting polymer, it is separated by some layer. So now the question is, the P dot PSS and electrodes are separated by dash. So the P dot PSS and electrode are separated by the oxide layer, like SiO2, silicon dioxide layer. So next we are moving toward the question number 21. Discuss the photolithography step. So we already discussed about the photolithography step. Like when at first we coated the device or the substrate using the positive or negative photoresist. Then after the coated with the after the substrate coated with the wafer coated with the positive or negative photoresist, we go for the which process we will follow. We go for the soft bake process, like at the temperature is 90 degrees centigrade for 1 minute, and if we use the AC weight, in that case the soft bake temperature is 65 degrees centigrade, and the time is depends on the thickness of the AC weight. And then we go for the UV expose, and after the UV expose, we go for the development process, and during the UV expose, the pattern is actually the photolithography is the pattern transferring process. So the pattern is transferring from the mask to the underlying layer or the photoresist. So what happened for positive photoresist, the covered layer, the covered portion is become harder, and the exposed portion become weaker. And for the negative photoresist, the opposite is happening, like the covered portion become weaker and the exposed portion become harder. So after the pattern transferring during the UV exposed from the mask to the photoresist, we go for the development process. So in the development process, the remaining photoresist is removed from based on the photoresist type and the mask pattern, like it is bright field or the dark field. Then we go for the hard bake process for positive and negative photoresist. The hard bake temperature is 120 degrees centigrade for 1 minute, and for AC weight, after the soft bake, we go for the hard bake process, which is the temperature is 90 degrees centigrade, and the time is depends on the thickness of the AC weight. And after the development, we go for another baking process for AC weight, and the temperature in that time is 125 degrees centigrade, and the time is depends on the thickness of the AC weight. Then after that, we go for the etching process, like if we go for patterning the chromium gold. So in the upper portion gold is present, so we at first we go for the gold agent. We use gold agent to remove the etching the gold, and after that we will use the chromium agent, and also we will follow the same process for AC weight also. So this is the photolithography step. So the next question is question number 22. How you will fabricate a piezoelectric pressure sensor? So go through the question. Actually, we already discussed this type of question in previous classes also. For your recall or and revise the previous chapter, we are discussing this type of question, that the fabrication step of the piezoelectric pressure sensor. So to fabricate the piezoelectric pressure sensor, what we do, at first we go for the at first we deposited their two process on the surface micro machining and also the bulk micro machining. So in the surface micro machining, what we have done, surface micro machining, we have deposited some oxide layer, and then the both side we deposited the oxide layer, and then we deposited the chromium and gold to pattern the interdigited electrode. And after that And we, if we need any micro hot um, at first we deposited the chromium gold, and after that we have to pattern this electrode. So we go for the photolithography process, and we already discussed about the photolithography process, that and then you can using the photolithography process, you can pattern the electrode. And from the back side also, at first we have to know what is the piezoelectric pressure sensor, and when we apply some force on the material, on the device, then there is a changes of the some electrical property like current or voltage as the output. So there we have to prepare some diaphragm type properties, some diaphragm type structure. So in the front side, when we go for the surface micro machining, we go for the photolithography process, and after that, from to prepare the diaphragm type structure, we go for the bulk micro machining. And for bulk micro machining, what we done, from the back side, then we go for the photolithography process. And from the back side, we have to prepare the mask, we have to design the mask according to it, and then we go for the oxide etching process, because in between the silicon wafer is present, and both sides the oxide. And so in front side, we go for the surface micro machining using the lithography process, and back side also we are going for bulk micro machining using the photolithography process. So from the back side, after we pattern transfer to the photoresist, then we go for the silicon etching. So silicon etching, we can use the buffer oxide, buffer hydrofluoric acid. And in that case also, backside there the silicon oxide is present, so we have to coated the backside portion using the photoresist to protect that side. And from the back side, we go for the BHF, we can dip the wafer into the BHF solution, then it will etch the silicon dioxide, and after that we can remove the photoresist layer, and then we go for the TIMA etching process. And using the TIMA process is a standard process, and we can etch the silicon wafer silicon we can etch. And also we have to optimize the parameter. So on the thickness of the diaphragm, we have to measure the thickness of the diaphragm. So by this process, we can etch the silicon wafer from the back side. So next question is difference between bright field mask and dark field mask. So please try to solve the question. So what is the difference between bright field mask and dark field mask? In the bright field mask, what happen, the pattern which we want to which we want, this is in the for the bright field, it is in the dark it is in the dark mode, or the chromium is present in that portion, and the maximum portion, the outermost portion, is in the transparent. So it is called the bright field mask. And what happened for the dark field mask, the opposite type of mask. It means only the pattern we need, it is in transparent mode, but the outside or the outermost portion is in the dark mode, or the chromium is present in that case. So it is called the dark field mask. Next question is, main three process of the MEMS fabrication are. So main three process in MEMS fabrication are, first is the deposition. At first we have to deposit, then what process we will follow. After the deposition, we have to pattern this process, because we want the electrode or something, so we have to pattern. And what is the patterning process called? It is called lithography. So we have to go through the, at first we have to deposit the material, so we will go through the process which is deposition. Then after deposition we will pattern. So the lithography process we will follow. So after the lithography process, what process we will follow? After the lithography process, we will etch, because using the photolithography process, the pattern is transforming from the mask to the underlying layer or the photoresist. Then after the development process, we have to etch that material, whatever we have deposited. Then we can get the proper shape, or the proper whatever we want the pattern, it will transfer to that material. So main three process of the MEMS fabrications are, first is the deposition, second is patterning for the lithography, and next is etching. Next we are moving towards the question number 25, which is not a MEMS fabrication process: wafer cleaning, deposition, patterning, or etching. So wafer cleaning is not the MEMS fabrication process, it is the additional process. This is the initial process. At first we have to clean the wafer, then we go for the MEMS fabrication process. And the main three MEMS fabrication process are deposition, patterning, and etching. So the wafer cleaning is the initial process, but it is not the main part of the MEMS fabrication process. Next question is, discuss about the RCA and RCA2 cleaning process. So what is RCA1 and RCA2 cleaning process? RCA1 and RCA2 is the standard cleaning process. So by RCA1 we remove the organic impurities from the wafer, or from the wafer, and by using the RCA2 we remove the inorganic or also metallic contamination from the wafer. So RCA1 is the we prepared by the mixture of the some chemicals like NH4OH, H2O2 and the DI water, and the ratio is DI water 5, and also the H2O2 is 1, and also NH4OH is 1. So DI water, H2O2 and NH4OH is 5:1:1. So using this mixture of this chemical, we prepared this RCA1. By using these chemicals, we can remove the organic contamination from the wafer. And what is the RCA cleaning? The RCA2 cleaning process. RCA2 is the standard cleaning process too. And by the mixture of some chemicals like the HCl, H2O2 and the some DI water, and the ratio of the DI water, H2O2 and the HCl is 6:1:1. So by using the RCA2 cleaning process, we can remove the contamination, inorganic contamination and ionic or metallic contamination from the wafer. Now next question is difference between piranha and tima. So go through the question carefully and then try to give the answer. So what is the difference between piranha and tima? All of you know that piranha is a cleaning process and tima is a etching process. So when we use the tima and when we use the piranha, you can remove the organic contamination from the wafer, and by using the tima we can etch the silicon wafer from the back side. When we go for the piezoelectric pressure or piezoresistive pressure sensor, in that case we have to prepare the diaphragm type structure. So for bulk micro machining we have to etch the silicon wafer. So in that case we use the tima. And by piranha process we can remove the organic contamination from the wafer. And how to prepare the piranha solution? It is the mixture of two solution like H2O2 and H2SO4. So we, and the ratio is the H2O2 and H2SO4 is 1:3. So by using this ratio, by using this chemical, by this ratio we can prepare the piranha, and we can dip the wafer into this piranha solution, and by this process we can remove the organic contamination from the wafer. So the main difference is the piranha is a cleaning process and tima is a silicon etching process, and it is a wet etching process. Wet anisotropy process. And you can recall also what is the anisotropy and isotropic etching. When we go for the isotropic etching, in that case it is the chemical is etch in all directions, so it is called the isotropic. In anisotropic, what happen, in a particular direction the chemical etch the wafer. So next we are moving towards the question number 28. What is annealing and why it is required in fabrication process? So go through the question carefully. So annealing is the heat treatment process. We can reduce the heat treatment process and we can reduce the defects by using this annealing process. Next we are moving toward the question number 29. What is the difference between contact and projection printing process? So when we are going to discuss the printing process, it is the part of the optical lithography process. There is a basic three types of optical lithography process is present. Like three types of optical lithography process are present, like the contact printing process, the projection and the proximity and the projection. So what happened in contact printing process? By this figure you can see, in the first figure you can see the contact printing lithography process, where the light, optical source and mask and photoresist and silicon wafer. So here we can see the mask and the photoresist is in contact. That's why it is called the contact printing photolithography process. And the proximity process, you can see there is a small gap between the mask and the photoresist. So it is called the proximity. So why we go for the proximity printing optical lithography process? Because if there is a gap, so the defects, when you go for the go for multiple time use of the devices, or multiple time go for use of this mask and the devices, in that case the defects are the chances of the defects are increases when you go for the contact printing photolithography process. But if there is a small gap between the mask and the photoresist, so there is a less chance of the defects in the devices. So, and the third one is the projection printing lithography process. What happened in that case? There is a lens is present between the optic mask and the photoresist. So what happened, we can go for the small size structure. It is actually, this lens is uses for the to overcome the limitation of the dimension. You can go for the 10 times smaller or smaller devices or structure, we can use it. And here from this structure you can see, when we use for the negative photoresist and when you use the positive photoresist, how the structure is where we can get the structure. For negative photoresist, the covered layer is remaining, and for positive photoresist, the covered layer is etched out, or it is dissolving, or this is weaker portion. And for the negative photoresist, the UV exposed portion is become harder, so it can remain. And the positive photoresist, the covered layer, the exposed portion becomes soluble and it is removed. This is the photolithography stage. And so last question is question number 30 is discuss about the different CVD and PVD technique. So we already discussed about the CVD and PVD technique. What is the full form of CVD? This is the chemical vapor deposition. And what is the full form of this PVD? This is physical vapor deposition technique. And what happened in CVD? There are different type of CVDs present, like the atmospheric pressure CVD techniques, also the plasma enhanced CVD techniques. Also there are different types of CVD, like low pressure CVD is present. And main principle of the CVD is we use some chemicals, and we also set the temperature, which is the melting of and the temperature is the above the melting temperature of the materials, and we use the argon flow. And when we give the temperature, it start to evaporate, and it start to react. And using the argon gas, using the carrier gas, it is deposited on the substrate. And what is the full form of the PVD? The physical vapor deposition technique. And there are different type of PVD techniques are present, like thermal evaporation, e-beam evaporation, and the sputtering. So what happened physically when we bombarded the what happened in sputtering? When physically the argon is bombarded onto the target, we have to maintain the environment also, that we have to set the temperature, and we have to set the pressure, chamber pressure. And also in case of sputtering, the argon is directly bombarded to the target, and it is removed, and the target is removed from that, and it is start to deposit some portion or material of the target is deposited on the substrate. And what happened in thermal evaporation system? There is a board, and the current the moving current going through the board, and in the board there is a source material is present. And what happened when we give when we follow the current through it, then it is heated, and then the source material is start to evaporate, and it is deposited on the substrate. And what happened in the e-beam evaporation? Actually, in the thermal evaporation system, there are some limitation, like the source, where we kept the source material. Now the source holder melting temperature should be below the source material. So this type of limitation we can avoid by using the e-beam lithography e-beam evaporation system. Like we can use the crucible, and we can directly pass the e-beam onto this substrate or the material, whatever we want to deposit. Then it start to evaporate, and it is deposited on the substrate. So we are ending our session here. Next we will meet next Tuesday 7 to 9 p.m. Thank you.